Okay, so I don't expect you guys to be able to draw these or recognize them or anything like that. I'm just showing these to you for your information. But this collection of 5 orbitals are what the d orbitals look like when you solve Schrödinger's equation. Over here, I've shown what the same, so it's what we call dxz, so it's the same orbital at different energy levels. So we can see in the middle, this would be like the 3D energy level. This would be like 4D, and this would be like 5D. So there is a node in between every single layer. But then also you'll notice there's really big empty spaces in between the same layer. So there's nodes within layers and nodes between layers, right? But each orbital, as you go up in energy level, stacks on top of the next one. And each orbital has the same number of nodes in it and between it. F orbitals are bananas, okay? Like, I don't know. This one I visualize as like a double pacifier stuck together. I don't know. But all 7 of these are the shapes of the F orbitals. Again, I don't expect you to draw them or recognize them really. Just have kind of a notion that the D orbitals have 5 possible shapes, which I called boxes before. 5 possible places to put electrons, so each one of these can only hold 2. They might be next to each other, or they might be across from each other. There's no rules. They might have one in the little ring in the middle, one in the top bubble, whatever, like that, okay? There's not any rules about where they are within this shape, except that they have to be pointing in opposite directions. But each shape represents the potential for 2 electrons to live there. Same thing for the F orbitals. That means the F orbitals can contain a total of 14 electrons in them, and the D orbitals can contain 10, because each shape can have 2. So 5 times 2 is 10. 2 times 7 is 14. Now when we solve psi squared, it turns out, and there's a really cool PhET simulation about this if you're interested in physics and chemistry. Again, not required, optional. But when you solve Schrödinger's equation, you get these shapes, and these here are actual images that we have managed to take that show where the electrons are at, right? And so each orbital is represented here. So this is when you have an n value of 2, an m sub l of 0, and an m sub s of 0. And so this is your first energy level, 1s. This is your 2s. Here we're seeing a 1s in the center. The node is the purple ring, and then a 2s, and then another node, and then a 3s. So on and on like that. So you can actually see the shape of these orbitals in this image. So as we're working through electron configurations, in order to get to the shape of a molecule, we have just 2 rules to follow. The first one just says that we have those 4 quantum numbers. No 2 electrons can have the same quantum numbers on the same atom. That would mean you have 2 identical pieces of matter, and that violates all of the rules of the universe. I'm pretty sure there's a lot of sci-fi stories written about having 2 identical pieces of matter and the consequences of that. Okay, we don't actually know what the consequences are because it's impossible. So when we're writing our electron configurations, we have to be careful not to violate that rule. The way that we write them is structured to help us not violate that rule, and also using the periodic table helps. Okay, so we cannot have the same 4 quantum numbers for any 2 electrons on the same atom. That's what Pauli says. Hund's rule says that if you have a choice in energy levels or shapes, however you want to think of it, the electrons would prefer to be aligned. So going back to our picture here, I said that you can fit 2 electrons in any of these shapes, boxes, if you will. So here's box 1. They could be anywhere in those lobes. Here's box 2. But here's the thing. It's like if you have siblings, right? If you have a really tiny house and a lot of siblings, you're going to have to share your room. If you have a really big house and you don't have siblings, you don't share your room. Electrons are the same way. So remember that electrons are repelling each other. And so what will happen really, and Hund's rule says, basically, if I have only one electron in the d orbital, it can live anywhere. It could be there, or it could be in any one of these other 4 boxes. If I have 2 of them, they could go anywhere they want. Any one of the empty spaces. And in fact, these electrons will trade between all these different boxes because there's nothing in their way, right? If I have 3, maybe I'll put one over here. If I have 4, like that, and if I have 5, like that. Now everybody is half full, and it turns out that a half full d orbital is actually really stable, which means they go down in energy, which is good. You'll notice that all the electrons point in the same direction. They're all pointing up. That's because that would be lower in energy than if 1 or 2 of them are pointing in opposite direction. So when we're doing our diagrams, we want to be careful to allow electrons to spread out as much as they can, but always point in the same direction. That's what Hund's rule says. We won't pair them up like this until we don't have a choice. Okay? So those are our 2 rules. And so we're going to look at a couple of Aufbau diagrams. Your textbook calls this something slightly different, but essentially we're showing where electrons are hanging out. And we always fill from the bottom up, lowest energy up. So Aufbau is German for fill up. We're going to start at the bottom and go up, right? So hydrogen has 1 electron, so it's going to be in the lowest energy level, and it could be pointing up. That's one way to do it, but it is equally correct to make it point down. They're both right. You get to pick. These are arrows. When I draw it on slides, I generally use half arrows because they're a little neater. You can do it however you want to. Maybe you have better handwriting than I do. I hope so. All right, so carbon. How many electrons does carbon have? Can you tell me? I hope so. It has 6. It's based on the atomic number. So we're going to fill in each box that represents a given orbital at a given energy level. And so the 1s is always got something in it. It has to, because it's the lowest one. In this case, if we need to fit 6 electrons, I'm going to have to fill this box first. Again, my arrow's pointing in opposite directions. Then I come up to the 2s, which is the next highest in energy, and that's going to be full. So I've used 4. I have 2 more electrons left. So in this case, I have 3 degenerate. Degenerate means the same energy levels. Okay, so these are all the same energy level. I have 3 degenerate energy level. So I could put it in any one of these 3, and each one of these is representative of those different shapes, right? So we got one that goes up and down, one that goes left and right, and the other one, that was poor. The other one actually comes out at us and goes back into the board, which is tough to draw, but most of the time the convention is we draw it kind of sideways to show, imagine that that's diagonal, to show that it's coming out at you. So we have 3 different shapes, all with the same energy level, and only 2 more electrons. So it has a lot of correct answers. That's one possible correct answer. This is another possible correct answer. Okay, so you can imagine that these electrons are not confined to one space. They can zoom into any of these 3 boxes. They're not going to pair up, though. It'd be like making, if you lived in a 5-bedroom house and you only had one sibling, you guys would not share a room. I wouldn't anyway. But electrons definitely won't because they're negatively charged. All right? And so this is another valid electron configuration that we might draw. Now we have a shorthand way of writing this because doing a diagram like this every time I needed to talk about how electrons are arranged would be very time consuming. So our electron configuration is going to be essentially just writing the energy level, the orbital shape, and the number of electrons at that level. So here we're going to say 1s, and the number of electrons is shown as a superscript. So 1s2. So 2 electrons are in the 1s energy level. And then we have 2 electrons in the 2s. And then we have 2 electrons in the 2p. And so with an electron configuration, you should be able to count up all of the superscripts to get the correct number of electrons that that atom has. In this case, 2, 4, 6. We did good. Okay. Another thing to note is that in hydrogen, all the energy levels are degenerate. Everything, the S and P, have the same energy as each other. That's not the case in carbon, and this happens because the electrons repel each other. And when electrons repel, that makes these energy levels different. Okay? That has important implications later. So I wanted to point it out. I'm going to give you the opportunity to fill this in. You can use Google Slides on a phone to write in your little electrons, or if you're on a computer, you can insert the shape as an arrow in each box as you need to. So don't forget about the Pauli exclusion principle and Hund's rule. So I reminded you about Hund's rule. These want to point in the same direction. What we would do, like, a mistake that gets made is, I'll do it in red. If I have electrons in the same box facing the same way, we would call this a violation of the Pauli exclusion principle. If I have electrons in the same energy level that are facing in opposite directions but in opposite orbitals, we would call this a Hund's rule violation. So watch out for those. You don't want to have the same atomic number or quantum numbers, and you don't want to violate Hund's rule. So always make your arrows spread out and point in the same direction, and you'll be okay. All right, so I want you to submit this in Module 5 as an assignment, so I can take a look at what you're doing. Either insert the shapes or draw on it using a tablet or your phone.